A multivariate analysis. That means we use a number of variables, more than two variables, to more than or equal to two variables rather, to model do the modeling work. So what we usually do is that we build a model to separate two or more classes, objects or categories. So discriminant analysis is more like a classification technique, like logit or probit model. To give an example, let's say we want to classify students into three categories. Our students are in the high school, and we want to know whether a student will go to college after the high school, or will go to a trade school, or discontinue the education after high school. There are three categories. um, there must be some pattern, right? Some pattern must be there between the different categories of students. And how do we categorize them? We can use discriminant analysis to categorize them. We collect information on family background, academic information, and use the linear discriminant analysis to find out whether a particular student is going to go to a college or a trade school, or is going to discontinue education. That is where LDA is used. One more example is we want to discriminate between a male and a female based on height. Well, usually the uh, average height of male population is higher than the average height of a female population. Okay, so there is a difference in the mean. So looking at the height, we can say that if a particular human being is a male or a female, we can be wrong sometimes, but most of the times we'll be right, or a majority of time we will be right. So height is one variable that discriminates between the categories male and female. So height is one variable. So we can have several variables. We can combine them, and then we can use them to discriminate two categories. That's how we use discriminant analysis. Let's learn about the theory. As I said, discriminant analysis is done by comparing the means of the variables. We take several independent variables, and then we see whether there is a difference in the mean for different categories. Like in the previous example, the mean height of male and female population is different. So height is one variable that explains the difference between the two categories. Similarly, we can have several such variables which explains the difference, and then we can club them and combine them in some way to come up with a score that discriminates between two categories. One of the assumption is that the variable that we are selecting, or the information that we are selecting, which will help us segregating the categories, should be normally distributed. So the independent variables should be normally distributed, and you know that to be distributed normally, the variable should be a continuous variable. So we cannot use categorical variables or the ordinal, that kind of variables in the LDA, limited linear discriminant analysis. And then there is an assumption of homogeneous variance. The variances of the variables should be homogeneous, so that is like the assumption of homoscedasticity. What is the computational method? The computational method is like this. We create an equation which minimizes the possibility of misclassification cases into respective groups. Okay, so iteratively we minimize the misclassification, and we choose the best set of variables, the best set of combination weightage, or the weights, in order to ensure that the misclassification is minimized. Mathematically, it involves a linear equation. You can see on the screen there is a discriminant function d, which is a linear combination of your variables, variables response score, and there is a set of weights a1 to ai. You have I number of discriminant variables, so there are I plus one number of estimates, um, pretty much similar to your regression coefficient, but not exactly though, but very analogous to them. And then you have a constant which is b in this equation. This the main purpose of the discriminant function is to find it out that how is the difference, what is the difference in terms of the expectation of or the mean of the different groups. Okay, based on that we categorize. So that essentially what is done mathematically. It's a very powerful technique, classification technique, but though the limitation is that that we cannot use categorical variables. That's one limitation. Pretty much like your logistic regression, order logistic regression, or probability regression, but classification techniques has its own advantage. You can have a best set of variables that that segregates blah 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 blah. Yeah, this technique is used in segmenting customers, segmenting patients, and then students. How do we segregate customers? We want to segregate into good customer, bad customers, not so good customers, or average customers. We segregate customers into bad customers, good customers. We segregate patients into high risk patients, low risk patients. So that is where we use the linear discriminant analysis, and that is where we use linear discriminant analysis. We will see in another session how to do it in SAS. In this video, I'll show you how to perform a linear discriminant analysis in SAS. To do that, I'll take a dataset from SAS help. If you go to SAS help, you will see this dataset iris. We'll take this dataset from SAS help to perform the linear discriminant analysis. This dataset is very popular. This dataset is used by Fisher himself. Fisher, the well-known statistician himself, for demonstrating the Fisher discriminant analysis. The same dataset we are going to use. The three things we are going to learn. There are three things we are going to do here. First thing we'll do is we will segregate this data set into two data sets: training data set and validation data set. In training data set, we will have training data set is the data set on which we will build the model, and then we will validate our model in the validation data set. And then once we have the two data sets, we'll build the model using proc_discrim. Proc_discrim is the SAS proc that is used for linear discriminant analysis, and finally we will validate the model. Let me first show you the dataset. I have taken it to my work library, so I'll show it from my work library. The name of my dataset is iris. This dataset has 5 variables. The last one is just the index. It's not a variable. I is just an index. Iris species. So there are three types of species in the flowers: setosa, and then virginica, and versicolor. So there are three types of flowers in the there are three types of flower, and what we are intending is we want to discriminate these three flowers based on the sepal length, sepal width, petal length, and petal width. So what essentially we are looking out for is to uh, to have a model, a discriminating model that will be used uh, to categorize flowers into the three species based on length, width, length of sepal, length of petal, width of sepal, and width of petal. Okay, so let us build the model. First, we will have the training and validation data set. We will use proc survey select, simple random sampling, and samp rate is 0.6. Samp rate is 0.6 because I'm taking 60% of the data for the training purpose or building the model. If you are not familiar with the sampling techniques, you can go through the video on sampling. Go to video on simple random cycling and stratified random sampling. Okay, let us run this. So total 150 observations are there. So out of that, we have taken 60% of that, which is 90. So 90 observation we are taking it for modeling purpose, and rest 40% of the data set will be used for validation purpose. We will not be using that for modeling. We will use the model to test whether the model is working fine in that data set or not. How do we create a validation data set? We'll just merge back. We will just merge back with the original data. 60% of the data we have taken it, and we just want the rest 40%. So for that I have used a merge statement in the data step, and I'm just merging the original data, the iris data with the iris underscore train data. Okay, so whatever is not there in iris underscore train will be there in the validation data. Okay, so essentially what it means is that train data plus validation data is equal to your main data or iris data. Okay, so iris data, which is the main data, is now divided into iris train and validate train data and validation data. Okay, and they are mutually exclusive. A particular observation which is present in training data should not be present in validation data. Okay, my validation data set is also created. Before I do the model, I must tell you that please go through the theory on discriminant analysis. There is another video on discriminant analysis. Please go through that before going through the hands-on session. You will know the theory of discriminant analysis. Just to remind you, discriminant analysis is a kind of statistical analysis which is used to discriminate between groups, categorize objects, classes into different groups or different categories. Okay, so it's a classification model, pretty much like logistic regression, order logistic regression. We have three categories here. Okay, three types of flowers we want to predict, or we want to segment flowers into species based on sepal length, sepal width, petal length, and petal width. These are the four independent variable or explanatory variable available with us, and based on which we will build a model which will predict but a particular flower will belong to which category. Syntax: proc discrim data, and then you have to mention the input data set. Iris underscore train is the training data set that we have taken. Outstat is dis, that means the output statistics will be stored in another data set. I have named it as dis. Method is normal, assuming that the independent variables are multivariate normal, or each one of them is distributed normally. Okay, there can be situation where there is slight deviation from the normality, and we have other options for that. But for this, the assumption is that variables, the independent variables, are all normally distributed. Then pool equal to S. One of the assumption is that the variable should have a uniform variance. Sometimes there is a deviation from this assumption, and if in that case we need to write no here. But in our data set, the variance is assumed to be homogeneous in nature. We can of course check these two things before doing the modeling. Okay, I'm assuming that you are familiar with the exploratory data analysis. So before building the model in any modeling process, first thing to do is to look at the data and then do the exploration on that, remove the outliers, make sure your independent variables are normal, because that is one of the assumption in linear discriminant analysis. Make sure that the variance is uniform for each of the variables. These two things are very important. um, and then once you are done with that, we'll straight away you can go ahead with the modeling. Then you need to specify the class is something but it's like the dependent variable in logistic regression or in multiple regression. Class, species, and then in var statement you have to mention all the independent variables or the explanatory variable ones. Okay, we have got four of them. Let us run this. You'll have a lot of output, but I'm not going to explain all the different tables that you can see in the output window. I'll only discuss the important ones. Initially you will have the information about the dataset, number of variables, number of classes, and the total number of observations. um, Yes, generalized square distance to spaces. That means how is the distance between the three different types. Remember, we studied in the discriminant analysis theory that linear discriminant analysis modeling is done based on the fact that there is a, difference in the mean for the different categories, mean of the variables for different categories. Okay, if you remember, we discussed about the heights of two individuals, and um, if the average height is you know average height of male and female are different, and based on the height you can actually tell for sure that whether somebody belong to a male category or belong female category. So height is one of the explanatory variable in that case. We discussed that in the theory video. So generalized square distance is that kind of statistic that gives how well separated the three categories are, and whether the explanatory variables are able to separate them well or not. And then followed by the discriminant functions. If you remember, we studied about discriminant function in the linear discriminant analysis theory video. uh, we discussed about the different coefficients, and you can see the coefficients, respective coefficients for the dependent variables, sorry, independent variable, along with the constant values. Okay, so this matrix is very important. This is a classification matrix. You can see the spaces names in the column as well as in the row. How do we interpret this? Setosa, you can see my pointer, and then Setosa here as well. It says that 27 observations are there in the dataset and 100%. Uh, that means all the observations in the data, the model is able to classify all the Setosa flowers in the dataset correctly. 100% correct classification. Okay, there is not even a single misclassification happening. Whereas if you go to here, this particular box, you will see that versicolor is classified as versicolor 93% of the times. Rest 6% of the time is misclassified. So couple of the flowers are actually misclassified as other flowers. Okay, so that is the accuracy rate. Similarly, Virginica, I can see Virginica, and then Virginica here also. 30 yeah, so 30 out of 30, so it means 100%. So all the Virginicas are classified as Virginica in the dataset. It might so happen that some of the observations be misclassified into different other types. So the goal of the algorithm is that to minimize that misclassification value. If you go down, you will see the misclassification table or the error happening there. For Setosa, the error is 0%. For versicolor also it's very negligible, 0.06. For Virginica it's again 0%. So what has happened is that some of the versicolor flowers are being classified as Virginica or Setosa. So that is what has happened. The overall misclassification is 2%. Okay, so out of the entire observation, 90 observation we have, only 2 observations or 2% of the observations are misclassified in our data set. So a model is a good model if the misclassification is as minimum as possible. Of course, the threshold value is something that is entirely up to you to choose where we need to put the cutoff. Okay. The next thing is that once the model is built, we try to validate the model. So how do we validate the model? We'll see whether this model is able to predict the categories or discriminate between the categories in the test data. What is a test data or what is a validation data? It's a data set that we have created which is not part of the training data set. Okay, it's a entirely new data set. If you remember, we did it in the first in the proc service select. Let us run this code. So for that you just need to write test data equal to validate. So validate is my test data, and this model what we build in the we built just now is going to be tested in this data set. Let us run this. So when you run this, you will have all the output that we just saw, and then we can directly go to the last segment, wherein it says that the classification summary for the work.validate data. Okay, what we saw earlier was on the training data itself, but what is more important for us is that whether the same model works in the validation data or not, because validation data is the new data. Okay, it's not part of the model data. Okay, it's a completely new data, and that is very important for us whether the model works in the new data or not. You can see the accuracy rate 100% for Setosa, 100% again for versicolor, and for Virginica it's 95%. So and if you look at the error counts, 1.6% times we see that there is a misclassification happening. So how do we know that our model is good or not, or whether the model is validated well or not? Well, in the training data the misclassification rate was 2%. In the test data or in the validation data it is less than 2%. So it's very much consistent. So the error happening, whatever error happening is very consistent across the model data, the training data, and the validation data. To make sure that your model is robust enough, you can create a lot of samples, new samples out of the dataset, and test whether the classification error or the accuracy error, whatever you call it, is consistent across all the data sets. Okay, so we can also do that, but from here also it appears to us that the error percentage is consistent, and hence the model is a good model. Okay, last thing that we will see here is that how do we save the classification values in a separate data set, and then how do we see how the classification is made. For that, you just need to add another thing to the above code. Along with the test data equal to validate, you have to create you have to name sorry, you have to um, use the test out data option. You have to use the test out option, wherein you will need to provide the out underscore val. Use test out data option to save your output for the validation dataset, and we will print it finally. Let us run this. Okay, so what we can see here is that we will see since we have printed the dataset, each observation you can see here the type of species here, and in the last you can see where it is classified into. Okay, Setosa is classified as Setosa, so that's a correct classification, and you go on looking at it wherever there is a mismatch. Okay, that is wrongly classified. Okay, that is the way it perform the analysis. We yeah, yes, there is very few misclassification. Most of the cases you will see uh, it's classified correctly. Okay, few points to note while doing discriminant analysis. Make sure that your data set is multivariate normal. You're using if you're using independent variables, sorry, I repeat, make sure the data set is multivariate normal. How do we check for that? You can do it in two ways. If all the variables, all the independent variables in our data set are normally distributed, then 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 the dataset is multivariate normal. Else you can use the mult norm macro available in SAS, which will directly will tell you that whether your dataset is multivariate normal or not. Okay, you can it plots a QQ multivariate QQ plot for you, and looking at it you can get to know whether your dataset is multivariate normal or not. Make sure you have checked for the heteroscedasticity problem, because that's also a serious problem. If it is there, then in the pool option mention pool equal to no. You should also do the exploratory data analysis before doing the model, to ensure that there is no outlier. The model is very sensitive to outliers, so misclassification happen because of the presence of outliers. Make sure you don't have it. To summarize, linear discriminant analysis is one powerful classification analysis that you can use to classify data into different categories. Okay, and three things are very important. Your data set should be having only. I stop. Okay, so that is about the linear discriminant analysis in SAS. Thank you.